Section 4.4 is comprised of word problems. Specifically optimization. We're going to find maximums and minimums. We want to find things like the least expensive, the most profitable. We want to maximize, one thing or another, and this is going to be called our objective function, whatever it is we're trying to maximize or minimize. And with that, we're going to be given a set of constraints. This means you only have so much money or so much time, so much workers' time, you only have so much materials, so much area, and given this set of constraints, you'll have several different constraints, then you're going to maximize or minimize that value that you're seeking. First up, we have a rancher is trying to maximize his area, I believe. Let's see. Yep, he wants to maximize the enclosed area, so that's what we're going to be looking at. What is my maximum amount of enclosed area? He's got a barn, and I know that he has 400 feet of fence. That's what we've got. And I'm supposed to use the barn as one side and then create 3 different corrals. Just giving it some variables. I'm going to have 1, 2, 3, 4 of these x's plus 1 of these y's. 4 of these x's plus 1 of these y's is supposed to equal 400 feet of fencing. This is what I was calling a constraint. And it is, I only have this much material. So that's a constraint. What I want to do is maximize the area enclosed. So this is going to be called our objective function, because this is what we're really looking for. I know the area enclosed is x times y. So I now have 2 functions. I want to maximize area, and we've been looking at maximum and minimum values using our derivatives. So if I want to maximize this area, I know that the points at which that happens would be I would take the derivative and then find those critical points, and that would give me the points at which I could maximize area. Now this would be a bit messy if I tried to do it as such. So what I'm going to do is I'm going to look at this constraint function, and I'm going to decide what would be easiest. I want one variable. So I could rewrite that constraint equation as y equals 400 minus 4x. And I could have written it as x equals and done the same exact thing that I'm getting ready to do, but it was much simpler as y equals, because if I wrote it as x equals, then I got to divide it by 4, and I don't like that. So let me just rewrite this with just x's now. So it's x times whatever y is, and that y is 400 minus 4x. And writing that in a neater fashion, that would be 400 minus 4x squared. So I want to maximize area. What I'm going to do is take the derivative with respect to x. So the derivative of a is then, looks like negative, oops, I forgot this little x here. Better put all of that in there. So it would be 400 minus 8x. Okay. Those critical points occur when the derivative equals 0. So 400 minus 8x. And solving this, move the 400 over, divide by 8x equals 50. So I can get either a maximum or a minimum area when x is 50. I look at the area curve and I see that what's going to happen is I will get a maximum value when x is 50. Alright, so next, what did they ask? They asked for the dimensions of the corral. Well, if x is 50, then y would need to be, hold up for just a second, 400 minus 4 times 50, so it'd be 200. So y would be 200, and that would make my area equal to 50 times 200. My area would then be 10 1,000, and this was in feet, right? So feet squared, my y needs to be 200 feet and my x needs to be 50 feet, so it needs to be a 50 by 50 foot by 200 foot corral. And I think I've answered the questions. Now let's look at the guidelines. Read the problem carefully. Oh, you know, this is my favorite part right here. Always draw yourself a picture. If you haven't drawn yourself a picture, it's really hard to figure it out. Identify the objective, we did that. Identify the constraint, we did that. Put it all in one variable, just makes everything so much nicer. And then we start playing with it and use our calculus to find the maximum or minimum points, and we did all of that. All right, great deal. Also of note is that it says here to check your endpoints. I really should do that, except I had exactly one critical point, and if I have one critical point, by our theorem that we covered previously, it said that I know that this happens to be a maximum or a minimum value. So I didn't need to check the endpoint on that. Well, I did kind of, because I used that theorem. Anyway, I'll do it on the next one. Next up, we have a box that we want to ship. A key part of this particular problem is that it is a square-based box. So I need to make sure that this is a square, so pretend. And then the other part doesn't really matter. Alright, so there's my box. And I know that this distance, we'll call it length times width times height. Of course, we can call them anything, but that's what we're going to call them. We know that the length plus the width plus the height must be less than 64, so we want our maximum volume, so we'll just say that it equals 64. The width and the height must be the same thing, so I don't care which letter you pick, but since these two letters need to be the same thing, we'll just make it W. So we'll just say plus 2W equals 64. Now I want the volume to be the greatest. This would be my constraint. My objective function is volume equals length times width times height. I'm making this length times W squared so I can reduce the amount of variables. Then this would be my objective function. Next, what I need to do is get this all in one variable. It looks like if I wrote this as L equals, wouldn't be too bad. I'm going to plug that in, this chunk right here. Plug it in there for L. So I'll get volume equals 64 minus 2W times this W squared. And my volume function is then 64 W squared minus 2W cubed. Now I plotted that for you with my little calculator. And there he is. Flatten this out. I made this from 0 to 40 counting by tens, and this was 0 to 10,000 counting by thousands. So 1, 2, 3, 4, 5 right there. Let you count the rest. Okay. I'd like to maximize volume. I'm going to take the derivative. This would be 128W minus 8W squared. I'd like to maximize the volume. That means I need to find the place at which the derivative equals 0 so I can get those critical points. Oops, there you go. That's a W. And it's 8W squared. And looks like I'll factor out that W. looks like I can factor out. I could factor out like a 2 would come out of it, and then that would make this a 64 minus, that would be what, 4W, is that right? You know what, 2 times 3 is 6. Did you guys catch that? I hope you did. I was like, what is the deal here? Something feels wrong. Okay, I'll fix that. There we go. W is either going to equal 0. Well, that would be a really skinny box then, wouldn't, if the width were 0, or W is either going to be equal to 64 over 3, which is not an even, it's just some little over 20 or so. Which, oh gosh, look right here, a little over 20 or so is where this maximum occurs. So if you want to, what you can do is you can do your little number line. If you need to prove it, this is what you do. Put this on the number line and you find these values and you say that using the first derivative test, to the left of 0, so choose something, say negative, that guy would be negative, and that would make this negative, so this would be a decreasing function from 0, in between 0 and 20, so we'll choose, say, a 10 here and 10 here, that would make that positive, it would be increasing. And then choose something to the right of 20, let's just say 30, something that would be in a reasonable dimension here. So that would be positive, and if that were 30, that would be like a 90, so that would make this negative. So this would prove that this is a maximum because I have an increasing function down to a decreasing function. So I know when the width equals 64 over 3, I've now proven that it is a maximum. So what's the dimensions? Well, I know that the width will be equal to 64 over 3 inches. The length would be equal to, let's see, 64 minus 2, 64 over 3. Crunching those values, let's see, the length would then be, I'd have to put that over 3. Hold on, I'll get that. Well, that just turned out to be 64 over 3 as well. Okay. And then the volume, so I know that the width and the height are going to be the same, so the height is in 64 over 3 inches. Then the volume needs to be 64 times the width, 64 over 3, quantity squared, minus 2 times the 64 over 3, quantity cubed. And for that, you get about, we'll just get this about value, this would be 9,709 inches cubed. There you go. I think I've answered the questions. What are the dimensions? That is length times width, length and a width and the height, and then what's the volume, and I gave all of that. All right, that one's done. This is a bit of a messy problem, trying to figure out what in the world they want you to do. So far I've got this pond and I'm standing here, so this is me, and all the way across, well, the radius is 1 mile, so we'll just write it like this, from here to here, 1 mile, 1 mile. I'm supposed to swim from here to some point P. Let's call it P here. I'm supposed to swim from here to here at a rate of 2 miles per hour. Then I'm going to get out and then I'm going to walk. Probably should do this in a different color, from here to here, so that I can get to the other side, because I'd like to swim and walk. And I want to do this in the shortest amount of time, and I'm walking at 3 miles per hour. And I want to know basically where do I have to be? Where do I have to swim to so that then I get out and walk and it would be the shortest amount of time? We get a different color. Alright. So let's choose, I don't want to choose theta because they have thetas over here, so I'm going to choose phi. So let's just say that there's that angle. This angle here would be pi minus phi. I need whatever this distance is, and this is in geometry terms called a chord length. That's why I snipped this guy, because we don't all remember our chord length and our arc length formulas, but I'm going to need that too, because the swim distance is basically a chord length. So the swim distance would then be 2 times whatever your radius is. Ours is a 1, that's nice. Sine of whatever our angle is. Well, we called ours phi over 2 because I don't want to have 2 different thetas being 2 different things, so that gets confusing. So our swim distance is then 2, because our radius is 1, sine theta over 2. So this is swim distance. Okay. Our walk distance is that arc length. Walk distance. Walk distance would be, it is, from here to here is pi, so if this one was phi, then this one would just be pi minus phi. The walk distance is arc length, and this will need to be in radians, but it would just be your radius times that phi. And our phi, oops, not that phi, times that angle is what I should have said, times that angle, which is pi minus phi. Alright, so walk distance is, our radius is 1, so it's just pi minus that angle. Alright, they didn't care anything about distance, they care about time. So I'll say swim time. Let me get this in swim time. Time is distance divided by rate. So I've got my swim distance, that's 2 sine phi over 2 divided by, and the rate that I was swimming is 2. That means my swim time is sine phi over 2. And then I need my walk time. Do the same thing. And it is your distance, which is pi minus phi over my rate, which is 3. Alright, now I need total time. That's swim time plus walk time. So it's sine of phi over 2 plus the walk time is, I'm going to bust that fraction, pi over 3 minus phi over 3. I can get my maximums and my minimums by finding the critical points, so I'll take the derivative of my total time, I'll call that big T. The derivative of this involves the chain rule. Take the derivative of the outside, that would be cosine phi over 2, times the derivative of the inside, that would be 1/2, plus, well, you wipe out because you're just a constant, and the derivative of this with respect to phi is minus 1/3. I need, in order to find the critical points, that this equal to 0, and 1 over 2 cosine phi over 2 minus 1/3, and I will end up with cosine phi over 2 equals, move that over, it would be 2/3. I'll take the inverse cosine of both sides, and I would get phi over 2 equals inverse cosine 2 over 3. Multiply both sides by 2 to get rid of this guy. Phi then equals 2 inverse cosine 2/3, which equals about 96 degrees. So it looks like I should have made my little dot over here a little bit more to make it a little more authentic. How would I choose P? I guess you could say that I would choose P so that it was 96 degrees. I want this right here, about 96 degrees from where I start is what it needs to look like. I guess I could say what that distance was. I could say that that distance might be an easier thing to get. So let me see, swim distance, I would say is 2 sine 96 degrees over 2. And if I do that, that swim distance is about 1.49 miles. So I'd swim about 1.5 miles and then get out and walk the rest. Okay, lovely. Alright, for this next problem, I'm going to draw my own little triangle here. I've got this 3-foot spot where I've got this fence, and over here's my house. That's our house. And this height here is 8 foot. And I want the ladder distance to be a minimum. I want the shortest ladder, so I want the ladder distance to be a minimum. So let's give ourselves some variables here. If I call this x, and I call this distance here y, my objective function is going to be L squared equals x plus 3 quantity squared plus y squared. A constraint, I've got this little triangle inside that big triangle, so I can use similar triangles here. So for my constraint, 8 foot is to y as x is to x plus 3. I want to get this thing in terms of y, get this out of here. Y is going to equal, plop you over to the other side, 8 times x plus 3 over x. Now I'm going to substitute you in here. This would be a really messy problem if I had to solve for L. And if I note the geometry of this problem and say that because L squared and my L are always non-negative, I'm going to have my extrema occur at exactly the same points. Let me rewrite this, do a little algebra, and make this look a little better. Now I'm not saying that looks good, but I did note that I had 2 of these x plus 3's in there, so I factored them out and then made it into this set of products here. So I'm going to take the derivative of L squared and just note that I'm going to have the same critical points. Now there is an error in their solution, so I'll go through this. I'm going to take the derivative of, I'm going to leave the first one alone, take the derivative of the second. It's going to pretend like this is just 64 to the x to the negative 2 power, which would mean that the derivative of this one is 0. Bring down that negative 2, that would give me negative 128 all over. Subtract 1 off that power, that would be x to the negative 3, so I'd have a 3 down here in the bottom, plus take the derivative of this first one, going to involve the chain rule, 2x plus 3, take the derivative of the inside, which is 1, so I'm not going to bother writing it down, 1 plus 64 over x squared. And then I'm going to simplify this a bit. Alright, just running that through with my algebra, noting that these two factors, these two terms then drop, leaving me with just an x plus 3 quantity squared, and then minus 384 over x cubed plus 2. And now I'm going to figure out where this equals 0 so that I can find those critical points. Of course, one of them is x equals minus 3, which doesn't make any sense, so I rule that out. So I'll solve for the other one, and I'll get minus 384 over x cubed plus 2 equals 0. And when I solve that, I get x cubed equals 192, and then x equals about 5.8 feet. What do they ask me? What's the length of the shortest ladder? Okay, so that means I need to go back to the length of the shortest ladder, which means I need to go back to here. Well, I'll go back and get my y, and then I'll plug it into here and get my L. So I plugged in, got my y, now I'm getting ready to get my L. Plugging all these values in, crunching them in my calculator. Don't forget to add your 3, as I almost did there at the beginning. Notice how I had a 5 there and changed it to an 8. I had to add that 3 because this was my distance for that distance from the house to the end of the ladder. So my ladder is 15 feet, and I now think I've answered all their questions. Good deal. If you have any questions, see me at the Collaborate.